Hello, everyone, and welcome to BigML's 2016 Summer Release webinar. So our last webinar was the spring webinar back in May when we officially released WisML, our domain-specific language for automation. So I've peeked through our logs since then, and we've deployed to production more than 70 times, which is roughly 4 deploys per week. Now, in amongst those little fixes, we've made some bigger improvements, and the one we want to highlight in today's webinar is logistic regression. So logistic regression is hardly a new algorithm. In fact, it was first introduced by David Cox way back in 1958. And it's even been a part of BigML since 2015, but previously only available through the API. With today's release, BigML's logistic regression implementation is finally beautifully simple to use. So what is it? Well, logistic regression is a classification algorithm, and as such, complements the existing BigML supervised learning algorithms. Now, it fits right in there with our models and ensembles of trees. Now, there's a lot of information that I just packed into that sentence, as well as a terminology surprise that we're going to need to deal with. So let's just start by quickly reviewing supervised learning. So in supervised learning, we have some training data, which comes in rows and columns. And that data is comprised of instances, traditionally thought of as the rows, that the algorithm is going to learn from. And each training instance has features that describe that instance. And then, this is the critical bit, there's a known label. So the presence of the label is what makes this supervised learning. That is, for each instance, we are providing the algorithm with the answers we expect so that it can learn a model which will ultimately be able to predict the label for new inputs. Now, supervised learning comes in two distinct varieties, classification and regression. The difference between these two varieties relates to the type of data that is provided in the label. For classification, the label is a categorical value, a discrete value, list of things, like red, green, blue, or elephant, zebra, hippo. This type of data is associated with models that predict things like, will this customer churn, true or false? What item should I recommend, shoes, pants, etc.? Or perhaps even, does this patient have diabetes? The other variety is known as a regression. For this type of supervised learning, the label is a numeric value. That is, it's some real number. And this type of data is associated with models that predict things like how many customers will churn, where we're looking for a number of customers. Or how much will this customer spend? Or perhaps even, what is your life expectancy? But in each case, the label, that is the thing we want to predict, is a number. So now that we've clarified the terminology of supervised learning, you might have a few questions. In particular, logistic regression is a classification algorithm. This means that the model is predicting discrete values. So how can this be a regression, right? How does that make any sense? And another fair question that you might be asking or might want to ask is, why do we need another classification algorithm? Right? BigML already supports trees and ensembles of trees, in particular random forests as well, which are extremely good performers across a wide domain of problems. They're scalable, easy to interpret, beautiful to visualize, and you can even export them and use them to make predictions in an edge location easily. So why add logistic regression? And maybe a few more questions too. But those are the big ones that we're going to tackle right away. So let's start with the first. So the answer lies in the fact that the algorithm uses a regression to build a classification model. That is, the regression in logistic regression refers to how the algorithm works and not the nature of the model that it builds. Okay, so to fully understand that, let's take a step back and think about regression problems in general so that I can connect the dots, literally. Okay, so the first example, which you may recall from taking a math class, is called linear regression. And the basic idea is, here are some dots that show the relationship between two variables. All right, in this case, we have a patient's tricep skin thickness on the x-axis there, and we have the body mass index on the y-axis. And given this plot, the idea is, let's draw a line through it, right? And we're going to try to choose a line that minimizes the error from all of these given data points. And you may not have known when you were solving for these types of problems back in your math class that this is basically a form of machine learning in a very narrow case. All right, because once you have the equation for that line, you can now predict a patient's BMI given their tricep skin thickness. All right, anywhere along that line, you can input a tricep skin thickness, and this line will give you a prediction for the BMI. There's nothing special about Bayesian line. In fact, we could try, some polynomial regression, which is also something you may have done in your math class. And in this case, we're doing roughly the same thing, but just trying to fit an equation of a line with some more nonlinear terms, maybe a quadratic or a cubic or something. We can keep playing this game, trying to fit whatever function we want to the data. But the key takeaway here with all of these regression techniques is that you are fitting some continuous function to the data. That is, we start with the assertion that there exists some function that fits our data, and then we try to solve that. All right, so one way that I like to think about this is that you're sort of making the universe the way you want it to be. You're saying, I know these variables should have a linear relationship, so I'm going to fit a line. As it turns out, this is also what logistic regression does. But what continuous function can we fit to discrete data? So let's make this a little bit more concrete with an example. So consider this plot, and this comes from the UCI diabetes dataset, which we'll play with in the interface as well. And what we're looking at is the result of the 2-hour plasma glucose test is plotted along the x-axis. And on the y-axis, we have whether or not each patient had diabetes. And I've added a little bit of color just for clarity. Okay, blue being that diabetes is false, and orange, the orange dots are all the patients where diabetes was true. And this is clearly discrete data, right? I mean, you've got only two possible outcomes, true or false. There's nothing in between. And so now we want to fit a function to this data. So we could try a linear regression, right? There's nothing stopping us from trying to fit a line to this. We might get something that looks like that. I don't know. I didn't actually try it, but we could, for the sake of argument, imagine it looks like that. And you can just glance at this and tell it's not a very good fit, right? This is probably not going to give you a very relevant result. Now remember, the game here is to start with a function that fits the shape of the data we expect. So what can we choose here? So if you guessed the logistic function, then you're right. And so speaking of old algorithms, the logistic function dates back to 1838 or so. It was originally introduced in a paper where they were modeling population growth. And it happens to have some rather nice properties for the problem that we are trying to solve. And so this green line here is a plot of what this logistic function actually looks like. And inside that box, there's the equation. And you can see we have some inverse of an exponentiation function. And as x becomes a very small number, right, tending towards negative infinity, we're going to take e to the minus some negative number, which is, of course, positive. And anytime you exponentiate a positive number, it becomes huge. So we've got 1 divided by some extremely large number, which is a very, very small number, right? So the logistic function is tending towards 0, not exactly 0, but very, very, very close. And likewise, as x becomes very large, as it moves out towards infinity, you're going to have e to the minus some very large number, which of course is very small. And now you're getting closer and closer to dividing 1 by 1, but the denominator is always a little bit larger. So it's never quite 1, but very, very close. And so we get this S-shape graph that I showed here in green. So now when we compare this to the data that I showed you on the previous slide, it looks pretty promising, right? I mean, you can kind of see that there's the logistic function is flat on the top and the bottom roughly, and there's kind of a space in the middle where it rises up to meet the other one. And you can kind of look at those blue and orange dots and say, the blue dots are shifted a little left, the orange dots are shifted a little to the right. It looks promising. But this still isn't discrete, right? I mean, the function has lots of values between 0 and 1 there in the middle of that graph. So instead of thinking about trying to model these discrete values exactly, let's think about trying to model probabilities. So what do I mean by probabilities? So let's take a look at this distribution of patient data again here. And in this little region on the left here, if I draw a box around it like that, it's pretty clear looking at that we have more patients in this little group here that do not have diabetes than we do have patients that do have diabetes, right? And so for this region, we have a sense that this is a region of a very low probability that you have diabetes. Okay, that's fair. So the probability is close to 0. In fact, if I had bounded that a little more to the left, you'd have almost no argument at all because you'd have no example of any patients that have diabetes. And if we extend this to the other side of the graph, and then the orange region now, we have the opposite. There are many more orange dots than blue, and we can see that this is a region with a higher probability of having diabetes. And then in the region in between, it's less clear. There's a mix of true and false, but we can understand that mixture to mean that the probability lies somewhere between 0 and 1. And so we can see that this looks like the logistic regression function will fit this very nicely, right? It's 0 on the left, it's values between 0 and 1 in the middle, and tending towards 1 on the right. All right, so remember, we're forcing sort of the universe the way we want it to be. So we could refine our understanding of logistic regression as follows. It's a classification algorithm that models the probability of the output class. So rather than actually trying to model the discrete values, we're going to model the probability of those discrete values. Now, this does have a few caveats. We're assuming that the output is somehow linear related to the predictors. Okay, that's important. Although we can fix this with feature engineering, which I'll show you an example of. And then, of course, we have the larger problem, which is how on earth do we even do this, right? How do we fit this logistic function to this real data? And we're going to tackle that right now. There's going to be some equations on the next slide. If you happen to be math phobic, please don't freak out. I'm only going to show them to you to give you a better insight into how logistic regression works, and more importantly, when it doesn't. All right, you don't ever have to actually solve these equations. This is exactly what the BigML platform does, but it helps to understand what's happening. So that said, here's the basic idea. So we're going to consider first just a one-dimensional case, just like the plot. So we're trying to fit some x values to some y values. And so we consider a linear function of x. All right, you can see it expressed inside that logistic function there. We have beta 0 plus beta 1 times x. And we just put that right into the logistic function. And we have a little bit of terminology here. Beta 0 is the intercept, and beta 1 is the coefficient of x. What we can do is we can actually invert this function into something called the logit. So we do a little bit of logarithms and a bit of messing around. And what we end up with is we get this natural log of the ratio of these probabilities. It's called the log odds. So this is the ratio of the probability of x against the probability of not x. And when we express the equation this way, when we show it in this more intuitive, friendly way, we can see on the right-hand side, we basically just have a linear function of x. And so now, expressed this way, you can see that we're basically just solving a linear regression again. That is, we're trying to find some coefficients beta 0 and beta 1 that will satisfy this equation. And the important takeaway here that I would like you to have for this logistic regression is that the output is those coefficients. That is the answer to the logistic regression model. Okay, you're going to give it some data, it's going to build the model, and what you get out is those coefficients. Now, of course, working on one-dimensional problems might be common in statistics, but not so for machine learning, where there tends to be this really feature-rich data, maybe tens or hundreds or even thousands or tens of thousands of features. So this is what I showed you here is only for one dimension. So how do we handle multiple dimensions? Fortunately, this is easy to extend. We just add more coefficients. So instead of just having a linear function there, we just imagine that there's e to the minus some function of x. And that function of x is still a linear expression, but it's a linear expression with a coefficient for every possible input variable or feature of your data set, if you want to think about it that way. So if we have k features, then we're going to end up with k plus 1 coefficients, right? One coefficient for each feature plus the intercept term. So that's enough with the math slides. Let's do a demo. Let's actually see this in action. And we can start with that diabetes example, and I can show you exactly what that looks like. So we'll take this data set. I'm uploading the source into BigML. I'll show you very quickly the data set in case you haven't seen it. This is from the UCI repository. And again, you have these 8 diagnostic measurements, right? So the number of times the patient was pregnant, their 2-hour plasma glucose, their blood pressure, et cetera. And then we have a categorical field down here, which is diabetes, true or false. And so using this data set, we can build a model that based on these diagnostic measurements can predict whether or not you have diabetes. All right, so I'll take this source and I'll make a one-click data set. And now to show you just a one-dimensional case first, I'm actually going to filter this data set. Okay, so I'll filter and I'll take out all of the fields except for the plasma glucose, because that was what we had plotted on the x-axis, and then the diabetes true or false. And so now I'm going to have a new data set that just has those 2 dimensions, and we can throw this in the scatter plot. And what this will allow me to do is show you that this looks exactly like the slide. In fact, when I made the slide, I just did a screen capture, except that I ignored, there's a few zeros in this data set that I threw out. But other than that, you can see this looks exactly like the problem description that I was showing you in the one-dimensional case of solving a logistic regression. Right, so here we have all the patients that do not have diabetes, and here are all the patients that do, and we're varying the plasma glucose along the x-axis there. So let's go ahead and apply a logistic regression to this. So I can just do a one-click logistic regression. And the what you're going to see at first is a plot. But before I explain the plot, I'm going to reveal the coefficients. Okay, there's a little button you can press here that opens this table view where you can see the coefficients. Remember, this is the actual output of the logistic regression. So we can see our intercept term has this is the value here, 0.76. And then we have a coefficient for the plasma glucose as well. So remember, this is a logistic regression in one feature, so we get these 2 coefficients out. But then there's also a missing entry as well. But this doesn't have any missing data, so that is 0. This is just something that we do for you to handle the case where this input might be missing as well. All right, so let's return to the chart for a second. So now you can see that this is a plot of the actual output of this logistic model. And the orange line here is the line that is predicting diabetes true, and the blue line is predicting diabetes false. And one of the little caveats of probabilities, if you don't know, is that they always need to sum to 1. So over here on the far left, when the prediction of diabetes true is near 0, then the prediction of diabetes false is near 1. They seem to cross over right around about 140, which you can see very nicely in this visualization. And so this region on the right here is where it's more likely that you have diabetes. Okay, and you can see the probability increasing as in response to an increasing plasma glucose level. Now, of course, we can use this model to make predictions. Just like any model, we only have this one input variable, but we can actually see in real time that for a plasma glucose level of 124, this model would be predicting diabetes false, and we have an associated probability here of 65%, and we can vary the plasma glucose input and see the same how that changes the output probability. So low plasma glucose, we have false, and higher plasma glucose, we have true again. All right, so let's go back to the full data set, though, and do this in a multidimensional case, right? It could be more interesting. So we'll take the original data set, and we'll just do a one-click logistic regression again. And now we're going to use all 8 input variables to compute this logistic regression. All right. And so now we start off with now instead of just having the one axis down here, we can actually choose the axis that we want to see. So we can do this it's a 2-dimensional plot, but it's of 1 dimension in the input. We can graph the plasma glucose, and we see a similar response as before. It's a little bit different, but now remember, this is a logistic regression with all 8 possible inputs. So what are the values of the rest of them when we're just varying this one? Well, they're controlled in the input fields down here. And so we can see that we have set of pregnancies as to 3 right now. We can vary this as well, and we can see how the logistic regression changes in response to that changing input in the graph of the plasma glucose. So we can actually slide this around, and we can see that as we increase the number of pregnancies, the crossover point is moving to the left, right? It's lower and lower plasma glucose where the probability is crossing over. And we can do the same kind of experiment with any of the rest of these sliders. And so this is one way that you can see how the logistic regression is changing for different types of inputs when you have a lot of inputs, right? It's very hard to plot 8 dimensions. We do, however, give you the ability to plot at least 2 dimensions. Okay, so we can see the response of this logistic regression in 2 variables at a time. And now this is a 2-dimensional plot, and the coloration is telling you what the output probability is. Okay, so anywhere that we're in this bright blue region down the left here, you can see that this logistic regression is predicting diabetes false with a very high probability of 98%. And over here in this orange region is back to true, sort of like the orange line before, also with a high. And then you can see that as we increase the plasma glucose, we're approaching this boundary where the probability is becoming more and more likely that you have diabetes until it finally crosses over into a positive zone. So this is a nice way to be able to see the boundary between the changes in this output class in at least 2 dimensions. Of course, we can play with this and see what this looks like with different variables, right? So I can change this to plasma glucose and BMI. And then I can also do the same thing we were doing before, where we can change things like the number of pregnancies to the blood pressure and see how that affects the boundary in the 2-dimensional plot. And of course, now if we go over to the table view, we expect to see many more coefficients, right? And indeed we do. We have our intercept term, the bias, but now we also have a coefficient for each input variable, all right? So this is the what the logistic regression essentially generates is these coefficients. So here you have one for the plasma glucose, one for the blood pressure, the tricep skin thickness, all the way down through the age, et cetera. And then an additional coefficient we throw in there for you to handle the missing case. All right, now I want to come back here, and I'm going to show you how this logistic regression is performing with an evaluation. So to do that, I need to do a training and test split so that we can train on one data set and evaluate with the other. And so I'm going to configure a training and test split. And this is actually one of the many deploys that we did. We added this little feature where you can actually specify the seed for the training and test split. This allows you to make training and test splits that are repeatable, right? So every time I put the same seed in there, I'm going to get the same 80-20 split. So this makes my experiments repeatable. And that actually is important in this case because for what I'm going to show you, I want to have this data set actually has well, I won't give away the secret yet, but there's basically some anomalies. And so I'll show you what happens. Okay, but now we have our training set. And what I'm going to do with this 80% is I'll just do a one-click logistic regression here. And actually, while that's running, I'll come back to the same 80% and I'll do a one-click model. And so what we can do is we can actually look at how a decision tree is pairing to this logistic regression for this particular data set. So as you will recall from the decision trees, right, we're getting this nice set of splits that will give us the best information gain. And this is now a very nice model. But let's go ahead and evaluate this. So we'll take the same 20%. And we'll do the same for the logistic regression. We'll evaluate this guy. And then I'll show these side by side. So I can do a compare evaluations. There you go. Okay, so on the left-hand side is the logistic regression. And remember, this is a classification algorithm. So when we do the evaluation, we get the standard classification metrics that BigML provides you, which is the accuracy, the precision, the recall, the F measure, and the phi. And what I did is I took that same 80% and I trained a one-click logistic regression and a one-click model, and then used the same 20% holdout to evaluate them both so that we can compare the performance of the logistic regression to a single decision tree on this data set. And you can see that in this particular example, the logistic regression is doing significantly better, right? It's got quite a bump over the single tree. And part of the reason why is because this data set, when you do that 80-20 split with the seed I used, ends up with a couple of anomalies in the training set. All right, they're outliers. And the decision tree is overfitting to those outliers. All right, it's trying to look at these anomalies and take them into consideration when it builds the model. And in so doing, it's lowering the quality of the model overall. And the logistic regression is a little better at ignoring those anomalies. Okay, it's not overfitting quite as badly. And I can actually prove this to you if we go back to our training set. Okay, so this is the same training set that we just used, this 80%. I can do a one-click anomaly detection. And this was going to build a model that will assign an anomaly score. So it'll tell us how anomalous each of the data points in this training set are. And one of the things we can use that model for is we can now filter out the anomalies. So I'll just take out these top 2 anomalies. These are the most anomalous points in here. And this is actually, this one is great because it has all these high markers for diabetes, like a diabetes pedigree that's super high, meaning there's a lot of diabetes in the family, super high 2-hour plasma glucose, but they don't have diabetes, right? So this is the luckiest patient in the world, but that doesn't help our model that's trying to generalize. So we'll take these 2 out, just those 2 anomalies, we'll remove them. Okay, and with this new data set that's now a little bit cleaner, okay, it just doesn't have, it's just missing those 2 anomalous data points. I'll do a one-click model again. and evaluate this. And we'll use the same 20%. And what you'll see when we compare this, bring up the other tree. All right, you can see just by removing those two anomalies, the single tree is still not doing as well as the logistic regression, mind you, but is doing significantly better, right? We're getting a 2 to 3% bump in all these metrics just by taking those anomalies out. And the reason why I showed you this is just to show you one of the things that differentiates logistic regressions from doing decision trees is the tendency for trees, single trees anyways, to sometimes overfit, and logistic regression to be a little bit more resilient to overfitting. Okay, so this is one of those differentiators. Now, of course, you can actually, for this data set, you can solve this with an ensemble as well that ignores those anomalies quite handily. But let's come back to logistic regression. So now I've been just doing one click, but of course there's lots of parameters you can control to impact how the logistic regression is formed. And so let me just give you a high level overview of what some of those are. The first is that there's an option that will disable the intercept term. Okay, so if you don't want that the beta zero, the bias term, you can just take it out. All right, you can disable that. This is important if the probability is not zero when your input is zero. Okay, and then we also have this idea of regularization, and this parameter controls how the logistic regression solution behaves. And the basic idea is that each iteration we have some penalty that helps control how large we allow the coefficients to become. And this helps control the variance. Okay, we don't want these super large coefficients because logistic regression will have too much variance. And there's a couple of different ways you can do that. There's this L1 regularization, and what this one does is it prefers to zero out individual coefficients. So it's going to let some of the coefficients get large, but it's going to try to hold some of the other coefficients closer to zero. And then we have L2, which prefers to push all of the coefficients towards zero. So how do you pick? Well, this comes down to, remember, we're trying to make the universe the way we want it, and it just sort of depends on which one gives you the performance you want. If I had to give you a heuristic, generally L2 works best and is also the default as well when you do a one click. Then we also have something called the EPS. And again, the way the logistic regression is actually solved, it's an iterative function. And so at each step, there's sort of a measure of the error. And this is just defining the minimum error, which tells the algorithm when to stop. You say, okay, once you've done step n, you do n plus 1. If the error hasn't improved by this much, then you're done. And then we also have auto scaling. And this will ensure that all your features contribute equally. Okay, and this is important because we're working with functions here. And so we can have scaling problems. You might consider modeling home prices based on the number of bedrooms and the square footage. All right, so you can imagine that the square footage is going to be, in general, a much larger integer than the number of bedrooms, right? You might have 4 bedrooms and 2,000 square feet. Well, actually, 4 bedrooms, probably 3,000 square feet. Okay, but the 3,000 is way bigger than 4. Okay, and that this relative scale of those inputs, the actual values that are in the input, is going to impact the behavior of logistic regression. Okay, it's essentially going to give the square footage more impact. And that's not always what you want, right? You probably don't want the square footage to be much more impactful than the number of bedrooms. You want them to be treated equally. And so to fix this, auto scaling is going to normalize all of the inputs so that they have the same scale, okay? And thus they'll have an equal importance during training. And, again, this is, unless you have a specific need, which is possible, right? I mean, it's very likely that you say, I actually want this variable to have a little bit more importance, and so I don't mind that it has this different scale, or maybe I've specifically constructed a scale so that it has more importance to the logistic regression. But that's a very narrow case, and again, comes down to exactly what you're doing. In general, auto scaling is what you want, and that is the default when you do a one click as well. It would be the general recommendation, unless you have a specific need. Okay, now a few more questions that have probably popped into your head while we've been playing with this. First is, how are we going to handle multiple classes? I mean, the diabetes example was great, but it's just a binary, right? Just two possible outcomes, true and false. How can we use logistic regression to model multiple classes? Remember, I had that example earlier with, I want a recommended item, is it shoes or pants or socks or whatever that the customer might want to buy? Okay, so how can we do that with logistic regression, more than just a binary outcome? And then another one is, okay, well, diabetes only had real valued numbers on the inputs, right? There were all these diagnostic measurements like number of pregnancies and blood pressure and tricep skin thickness, all numbers. What are we going to do about categorical inputs or text inputs or all these other possible inputs that BigML supports? How does logistic regression handle those? Okay, so first let's consider what we're going to do about multiple classes, okay? So remember the idea here is instead of true, false, maybe we have like red, green, blue, okay? So we have some model or logistic regression model that wants to predict between these three possible outcomes, okay? Could be any three things or four things or however many. And so in the general case, let's just assume that you've got some K classes, okay? So your output that the logistic regression is trying to predict has K possibilities. What we're going to do is we're just going to solve K one versus rest logistic regressions. Okay, so we're just going to solve logistic regression K times. And what we're going to do is solve it for one class versus all the rest. So in the red, green, blue example, we would just solve a logistic regression for red and not red. That's a binary outcome. And then we would solve another one for green and not green. And we'd solve another one for blue and not blue. So with those three classes, we would end up with three logistic regressions. Each one is a binary outcome, and now we can combine them together. Okay, so that's the basic idea. We would just, if we have K classes, we do this K times. And the important takeaway here is that the result is going to be a set of coefficients for each of the classes. So we're just going to get a whole bunch more coefficients, right? That's the basic idea here. But that's no problem. Okay, we can handle more coefficients. Okay, so now let's consider how we're going to handle categorical inputs. All right, so remember that logistic regression is expecting numeric values. So one idea is that we can convert the categorical input to a numerical input by an encoding, right? And there are various encodings that you can use. The first that we'll consider is called one-hot encoding. And the basic idea here is, so now, and I'm sorry about using red, green, blue to hopefully that won't confuse you. With the last slide, I was talking about red, green, blue being what we were predicting. In this case, I'm talking about red, green, blue being an input. So we have some input variable that's a class or a categorical value that can be red, green, or blue. It's something that's controlling what we're going to predict. And the idea is, how do we handle that? Well, one thing we can do is we can just add new features to our data set. We can have one feature that's just called, you know what, the color is red. Okay, and when that categorical value is red, we'll put a 1 in that column and a 0 in all the rest. All right, and when it's blue, we'll put a 1 in the blue column and a 0 in all the rest. And you'll notice we've also added a color equals null. Okay, this is to handle the possibility that feature where I have requested the color, there's no input, right? So we would just take the original color feature, becomes these 4 new features, 1 for each class, in this case only 3, plus 1 for it could be missing as well. And this works. And the basic idea here is that there's only one feature is hot for each of these classes. So that's what's called one-hot encoding. Okay, we can do a slight variation on this. There's another technique called dummy encoding. And this is similar to one-hot encoding, but we use the realization that we don't really need a separate feature for each possible class, right? We could start by just choosing some reference class, and then we would be adding one less degree of freedom. Or instead of adding 4 features, we can get away with just adding 3 by choosing this reference class. In this case, it's the one asterisk there. We've said, okay, red is our reference class. So when it's red, I'm going to add these 3 new features, color 1, color 2, and color 3. And when it's red, they're just all 0. And when it's blue, I put a 1 in the color 1 column. When it's green, I put a 1 in the color 2 column. When it's missing, I put a 1 in the color 3 column. All right. Now this does change the way logistic regression is going to interpret this. The way it does that, rather than treating all these classes equally, the logistic regression is sort of comparing the possible classes against the reference class. All right. So this makes sense when you have one class which is really dominant. You can imagine that it just occurs way more often, or when you specifically say this is the thing I want logistic regression to distinguish from. Okay, this one type of class or this one output here, or input, sorry. I want it to be sensitive to when it changes away from this reference point. Okay, so it's a slightly different use. Okay, we can sort of take the logical extension of dummy encoding and say, you know what, I don't even really need to add 3 columns. I could just literally change all of my possible categorical values into numbers, right? No problem there. So in this case, I would set red to 0.5 and blue to negative 0.25 and green to negative 0.25, and the null could just be 0. That seems reasonable. Okay, and this is called contrast encoding, and it has a little bit different impact on the logistic regression. Basically, what's going to happen is that this creates a certain influence for these possible input classes. For the red, because we've specified this positive number, it's going to essentially have a positive influence, and the two negative numbers are going to create a negative influence. And anytime you put a 0, it's just going to be largely ignored. And now the thing about this, there is a little bit of a caveat here. You can't just pick these integers the way you like. The field values, okay, that you choose for each of these classes need to sum to 0. Okay, I don't mean across all the inputs. Like if I had 3 reds, I don't have to worry about that being 1.5. It's just that the values I choose for each class has to be 0. So in this case, 0.5 minus 0.25 minus 0.25 plus 0 is 0. So this contrast encoding would work just fine. Okay, so how do you know which encoding to choose? Well, again, there's no right encoding, right? It just depends on what you're trying to do. Remember, we're making the universe the way we want it to be, so it's very specific to the data you're working with. So there could be a situation, you're working with logistic regression, and you know you want to force a specific behavior, and you simply just need to know what happens when you change it, and to know that that's the behavior that you want. That's really the best answer. Okay, so what about text? Well, the text items is another data type that BigML supports. When you give us unstructured text, we do something called a bag of words analysis. And so what's going to happen with that analysis actually lends itself to logistic regression very well. Okay, so we're going to take this new input feature that's just got text in it. And what happens is that we do something called word stemming. We remove all the words that don't occur very often and all the words that occur too often. And you sort of end up with this meaty set of tokens that represent your text. And what you have is frequencies. And so you might imagine this example I've got, maybe this is reviews for a Safari adventures, okay? And so every text input is some review that somebody wrote on a website about a Safari adventure. All right, and so you can imagine that when we do this text analysis, we're going to have these frequencies, and the word hippo is probably going to occur in there because it's Safari. Okay, and so in training instance number 1, the word hippo occurred 3 times, the word Safari didn't occur at all, and the word zebra occurred once. And I'm only showing you 3, but what actually happens in this text analysis is that you'll typically end up with thousands of these features. We generally hide them. You don't see them in the data set, they're just in the background, although when you're looking at a text field, you can actually see the tag cloud and show you the word frequencies. But the basic idea here is that this already lends itself to logistic regression very well, because the text fields are going to be converted into these token frequency counts. So let's see another demo. All right, and this time I'm going to use a data set that has user preferences. And this is basically like a survey that was done. And there's a bunch of questions in here. There's some information like the latitude and longitude of the person that was filling this out. Okay, they have some information here like, are you a smoker, true or false? What is your drink level? Do you abstain? Or are you a social drinker or a casual drinker? What type of dress do you prefer, informal or formal? What type of transportation do you prefer, walking or public transportation? Okay, but there's a bunch of profile information in here that people have filled out. And so we've got a nice mixture of categorical and numerical values. And so we can play with this a little bit with logistic regression. So I'll go ahead and make a one-click data set first. And what I'm going to do is, this time, instead of doing the one-click, I'm going to configure. And so now we can actually explore some of the configuration options that we've been discussing. So we see the objective field I can set. So in this case, what we'll do is we'll try predicting the drink level. Okay, we'll try to figure out whether or not people prefer to abstain or be casual or social drinkers. And you'll notice we have a default numeric value. Okay, so if you have numeric values that have missing values, you can set a default for them. This is much like our clustering algorithm. You don't have to do this, right? There's other ways to handle missing values, but if you want to have a default rule for missing numeric values, you can set that here. We also have that EPS criterion. It's right there. In the advanced configure panel, if we open that little slider, you can see under the scale section, we have the toggle to exclude the bias term, right, if we don't want that. And then auto scaling is on by default, so we could turn that off if we wanted to. We can change the regularization here. We have the L1, L2, and there's also a strength, which I didn't discuss, but is described very nicely over here. Then we also have the field codings. Okay, so where are these configured? Well, when we come down here to the fields, you can see there's a little gear next to each one. And any of these that are categorical, since I'm defining a logistic regression, I can just come in here and click on this gear icon, and this is where I would configure the field encoding, how I want the logistic regression to handle this categorical input. Okay, so by default, we're going to do one hot encoding, but we can set that little slider there, and now we can do the dummy encoding, or we can do contrast encoding if I want to do specific values for each of the possible classes. In this case, this is just a true false, but I could do a 0.5 and a minus 0.5 or whatever you want to do in here. So that's where you configure that. For this example, let's take all these features out, and let's leave this in, and the latitude and the birth year, which is relative to your age. So we're going to try to use a logistic regression to predict what level of drinker you are based on your latitude and whether or not you smoke and the year you were born. Okay, so let's see what that does for us. And so now, because we have, remember, this is now a multi-class problem. It's not a binary class, right? So we have 3 possible outcomes. You can be somebody who abstains, you can be a casual, or you can be a social drinker. Okay, so we end up with 3 graphs now. All right, and so this blue line here is the people that basically abstain, and the red line are the casual drinkers, and the green line are the social drinkers. And what we're looking at here is a graph of the latitude. Okay, so we can see that people who abstain is pretty flat across all latitudes, whereas the social drinkers are increasing probability with higher latitude. So northern latitude seems to be more likely that you are a social drinker and less likely that you are a casual drinker. So that's interesting. Of course, we can change the birth year and see how this changes, right? So if you're older, it seems to be that you're more likely that you abstain from drinking, which is interesting as well. Okay, we can also try changing the input if we want to see what happens if we only consider, or if we consider people who smoke instead. We can change that categorical value. And what you can see happening there is that the people who abstain goes from 50% probability almost down to 10%, whereas the way the other 2 graphs cross over with latitude isn't really changing, right? We see the social drinkers are increasing with latitude, and even for the smokers, that's also true. Social drinking is increasing with latitude, although much more aggressively now as well. Okay, but interestingly, it seems that people who smoke are less likely to abstain from drinking. So those seem to go together. Okay, and of course we could do this in a 2-dimensional plot as well if we wanted to see how this varies in 2 dimensions. Okay, and if we look at the coefficients, that's the other thing I want to show you. We now have 3 possible outcomes. So remember, there are only 2 columns here before. I forgot to mention that they were the opposites, right? So one was just true and one was false, and so they were always just the negative of each other. But now we have 3, and so we have slightly more interesting. We have a column here for the people who abstain and the casual drinkers and the social drinkers, and then we have a coefficient for each of our input variables. Okay, we have the latitude, and you'll notice what's happened to the categorical value, right? That used to be just true and false. It's become 2 possible inputs, right? So this is that one hot encoding. There's smoker equals false and smoker equals true. So those are the 2 possible outcomes. And depending on which one it is, it puts a 1 into that column. And so you end up with 2 coefficients for that categorical. If we had K classes here, there'd be K new coefficients, 1 for each possible encoding of that categorical value. All right. I want to very quickly talk about more complicated shapes. So we have this idea of a curvilinear logistic regression. So what if we had a distribution that looked like this, right? This doesn't look like what we had before. We've got a case where we have, 1 values, and then we have some 0 values in the middle, and then we have 1 values again. And you can try imagining the logistic regression fitting that. It's going to fail horribly, right? So how do we deal with this with the logistic regression? And don't worry about the fact that this might feel like we're cheating. We're not. Don't worry. Because remember, we're trying to make the universe fit the way we want to. And you have a sense looking at this that this looks more like a quadratic function, right? I could fit some kind of parabola to that. That would work better. And you can then use that insight to say, you know what? Instead of solving a linear equation in X, I could just add a feature in my logistic regression, a new input variable, x2, and I would just define that x2 to be the square of x1, and that gives me my quadratic term. And this actually works very well. And you can do this with higher order terms or other functions to sort of force your logistic regression to match the shape of your data. And I'll show you an example of this very quickly. So I'll take a new source. So we have this quadratic demo. Let me go straight to the data set. And I've given this data set is synthetic. Okay, I just created this values, but to give it some context, I labeled these as age and severe case. And so you could imagine that this maybe represents the likelihood that you have a severe case of the flu based on your age. All right, so here we see a group of people who are much younger, all right, less than 10 or so, that are all having, or more likely, there seems to be more incidences of severe cases of the flu for young people and old people. And then we have a distribution down here of people who did not have a severe case. So these all people had the flu, but it's whether or not it was severe. All right, we can see that we're getting this quadratic shape again, right, where there's that I was showing you in that plot before. So let's go back to our dashboard, and what I'm going to do is add my quadratic term to this data set, which I can do very easily with an add feature to this data set. So I'll add a field, and we'll call this age squared, and we'll take the square, okay, of the age, and that's all I need to do. Okay, this is just going to add a new feature called the age squared. All right, now to show you that this performs better, I'm going to need a training test split so I can show you the evaluation. So let me just take the defaults for the training and test split. And now I'm going to make two logistic regressions. All right, one not using the age squared, so just using the age. And we'll let that run. And we'll configure a second logistic regression using both the age and the age squared. And now if we come back to the first logistic regression I made, this one, we can evaluate it. Oh, and everything's orange. Okay, so we can see right away this is not doing very well. The accuracy is basically the mode. Okay, so this is basically a model that just says everybody's going to be fine. No one's going to have a severe case. That's probably a bad sign. Let's go back to our logistic regression that has that quadratic term in it. And then we'll evaluate this one as well. Okay, this looks much more promising. And I'll put these up side by side for you. All right, and so you can see on the right-hand side is our logistic regression built without the quadratic term, and on the left-hand side is built with that quadratic term. And again, this isn't cheating, right? Our data just has a shape that the logistic regression can fit better when you provide it this feature engineered, this quadratic term. And this turns out to be something that you can do, a little game that you can play. There's no reason to not try it, right? You can try a quadratic or a cubic term and just see if it does, if logistic regression does better. That's a perfectly valid approach. All right, so let's summarize a little bit. This is an attempt to answer that very first question I asked, which is why add another classification algorithm? How do we differentiate logistic regression from the decision tree? And so first, logistic regression really expects this smooth linear relationship with its predictors. All right, that's a very important distinction because the trees, they adapt really well to these ragged nonlinear relationships. Okay, which I'll explain. And logistic regression, again, remember, it's concerned with the probability of some binary outcome. Okay, it's a very narrow focus. You're looking for well, of course, you can do multi-class, but then you're doing multiple logistic regressions. But still, as an algorithm, it's a very narrow use case. All right, whereas the decision tree has no concern. Classification, regression, multi-class doesn't matter. You just throw the data in there, the decision tree builds its model, and it's all good. All right. Logistic regression has lots of parameters for you to get wrong. Right, you've got all these choices you can make: the regularization, the scalings, the codings. Do you need to add these quadratic or cubic terms? There's lots of places you can go horribly wrong with logistic regression. Whereas the decision trees are generally, they're parameter free. There's nothing to do. You put your data in, and a tree comes out, and it's all good. Okay, now so far the decision tree is looking like, why would you ever use logistic regression? So let's give logistic regression a few points here. Yeah, it tends to be slightly less prone to overfitting. I know that's a bit hand wavy. But that's the way it is. Depending on your data, it is generally less prone to overfitting, whereas a single tree is slightly more prone to overfitting. And again, there's ways to solve that, right? We saw one using the anomaly detector to take out anomalous data points. That helps. Another is to use the ensembles, right? To do something like a baggy ensemble or a random forest. Those are less prone to overfitting. Okay, so those are ways to give the decision tree a fighting chance there. And then another one is that logistic regression, remember, it's fitting a shape. So sometimes it might work better when there's less data available. So if you have a very small data set and the logistic regression is going to fit the shape of your data well, the surface boundary between the probabilities, then it's going to outperform the tree. All right. The corollary to that is the decision tree. It's got these sort of two ideas. One, it prefers these splits that are parallel to its parameter axes, okay, which can cause it problems. But as long as you give it enough data, it's going to discover any shape. Okay, so there's kind of the two things here, right? If you don't have very much data and you know what the shape is supposed to be, right? Imagine if I told you the shape is the equation of a line, you don't really need that many points to define the equation of a line. Okay, and that's sort of what you're doing with the logistic regression. You're saying, I know it's the shape, I can give you a very small data set, and I can now fit it, and I'll probably get good results. Whereas a decision tree, you're going to need a little more data. And just to make that concrete, if I gave you a shape, a decision boundary that looked like this, what's going to happen with the decision tree is it's going to try to make a split somewhere in here, separating these two classes. Maybe it picks a split that looks like that, x less than about 0.5 or so. But you see, it's having trouble finding that diagonal boundary because it can only make x and y splits. And maybe it'll make another split here, and then maybe it'll make another split there. And finally, it's isolated that quadrant in the upper left-hand there. It's all orange. But now it has to do this over and over for each one of these regions. And you can see if I only gave you like 3 or 4 or maybe 10 data points, it would have trouble finding that diagonal shape. But as long as I give it enough data, like in this picture, it's just going to keep splitting until it discovers that diagonal boundary very well. And so that's a good example of, as long as you have enough training data, the decision tree can find these decision boundaries that are not parallel to the axes. Okay, so that's it. That is a introduction to BigML's logistic regression. And now I'm going to turn it back over to Atakan for a couple of wrap-up notes.
Thanks, Paul, for the detailed presentation. I'd like to mention our education program. We launched this about a year ago, and to our surprise and pleasure, a lot of people have taken advantage of it. At this point, we have 78 BigML ambassadors that have signed up online. If you go to bigml.com/education, on that page, you can sign up as a BigML ambassador for your campus, for your university. As you can see, we have participation from all around the world. In addition to the ambassadors, we have over 600 universities being represented as part of our user base today. So we're very happy about the way BigML is being adopted in education institutions, and we'd like to promote that further. In that regard, what we offer is a free BigML Pro subscription plan for a year. That's a $300 value for free. And in addition to that, we will help you promote BigML and machine learning in general on campus. If you have any event ideas or meetups or special assignments or study groups that you have in mind where machine learning help, we're always happy to work with you closely. Again, we're pretty amazed at the level of creativity some of these ambassadors do come up with, and we're always happy to help. We can also pass you some BigML merchandise to help promote learning in general and BigML in classrooms. So there are a lot of different opportunities for you to make a difference, not only in your own discipline, but also in the lives of your colleagues or students on campus. So please pass on this promotion to your peers and those that may be interested in your geography. And thanks for being part of the BigML community.